everyone. In this plus 2 class chemistry video lesson, today we are going to study about the conduction of electricity in semiconductors. We have already studied that in semiconductors, the energy gap between the valence band and the conduction band is small. So the thermal energy available under ordinary conditions is sufficient to excite some electrons from the valence band to the conduction band. Thus, only a small amount of current can flow through them. The conductivity of semiconductors depends upon the temperature of the material. At absolute zero, semiconductors are perfect insulators, but at room temperature, there is enough thermal energy to allow the electrons to jump, and this gives the semiconductors limited conductivity. Semiconductors can be classified into two categories: intrinsic semiconductors and extrinsic semiconductors. The semiconductors which can conduct electricity in their pure form are called as intrinsic semiconductors. These are composed of only one kind of material. Silicon and germanium are two examples of intrinsic semiconductors. They are also called undoped semiconductors. The conductivity of silicon and germanium is very low at room temperature because of absence of free electrons in them. This is because silicon and germanium crystallize in diamond-type network lattice in which each atom is bonded to 4 other atoms. However, at higher temperature, the bonding starts to break and electrons are ejected which are able to move through the structure, and it increases the conductivity. The process of adding small amount of impurity to an intrinsic semiconductor is known as doping. The semiconductors which are formed by adding impurity to an intrinsic semiconductor are known as extrinsic semiconductors. For example, when germanium is doped with arsenic as an impurity, it becomes extrinsic semiconductor. Doping can be done in two ways: with electron-rich impurity or with electron-deficit impurity as compared to the intrinsic semiconductor. Such impurities produces electronic defects in semiconductor and produce an N-type or P-type semiconductor. Let us firstly study about N-type semiconductors. Both silicon and germanium belong to 14th group of the periodic table and have 4 valence electrons each. When silicon or germanium is doped with small amount of group 15 elements such as phosphorus, arsenic, its electrical conductivity increases. In pure silicon or germanium, each silicon or germanium atom uses its 4 valence electrons for the formation of 4 covalent bonds with the neighboring silicon or germanium atoms respectively. When silicon or germanium is doped with some group 15 elements, then some of the positions in the lattice are substituted by atoms of group 15 element. The group 15 element have 5 valence electrons. After forming the 4 covalent bonds with neighboring silicon or germanium atoms, the 5th extra electron is free and gets delocalized. These delocalized electrons increase the conductivity of silicon or germanium. As the increase in conductivity is due to the negatively charged electrons, the silicon or germanium crystals doped with electron-rich impurities are called N-type semiconductors. Next is P-type semiconductors. Electrical conductivity of silicon or germanium can also be increased by doping with group 13 element such as boron, aluminium or gallium. Group 13 elements have only 3 valence electrons. When silicon or germanium is doped with some group 13 elements, then some of the positions in the lattice are substituted by the atoms of group 13 element. As group 13 elements have only 3 valence electrons, they can form 3 covalent bonds with the neighboring silicon atoms. One of the valence electron of the silicon remains unpaired and a hole is created at the site where 4th electron is missing. This is called electron hole or electron vacancy. These vacancies are commonly known as positive holes. To fill this vacancy, an electron from the neighboring atom jumps into the electron hole, creating an electron hole at its original position. When the electric field is applied, electrons migrate towards the positive electrode by filling the holes making it appear as if electron holes are migrating towards a negative electrode. These holes are responsible for electrical conduction, and the resultant semiconductors are known as p-type semiconductors.